Hello everybody, welcome to my video. Today we're gonna be doing, this is the preliminary design of the column. This is the typical floor framing plan. This is from ground floor, second floor and third floor. This model building is a 3-story building with basement, and all the floor framing plan of this building are typical. They're all the same, like this one here. They have the same spans of beam, 6 meters each along the longitudinal direction, and for the transverse direction it has a 5-meter span of beam. To design the column, you need to locate our tributary area, and you have to make sure that that tributary area has the maximum area. Looking at this frame here, all of the interior columns have the same tributary area, so I choose one right here, and then I draw the illustration right over here so we can analyze and design the column. So here's the column. The column is carrying 4 1/4 piece of slab. The total of that is the one whole slab of 6 meters by 5 meters, and that is the tributary area of the column. 5 times 6 equals 30 square meter of tributary area. The column is carrying 4 1/2 beam. The two of them has 2.5 meter span. This one and this one, and the other two has 3 meter span. You have to calculate all the weights, all the materials that carried by the column, the slab and the beam, and plus the live load. Okay, now loads carried by the column. From preliminary design, we have letter A, dead loads, and letter B, superimposed loads, and letter C is the live load. Superimposed load is also considered dead loads, but this type of load is imposed after the construction is finished. Here's the design requirements. Structural sizes from preliminary design are: beam. The width of beam during the preliminary design we found 440 millimeter, and the depth of beam is 930 millimeter. Here is the beam that we previously designed. 440 is the width, and the depth, the effective depth, 880 millimeter. And since we need to calculate the total weight of the beam carried by the column, we need to add this concrete covering here, which is 50 millimeter. The 50 millimeter is the minimum requirement specified by the ACI code. So we add this 50 to 980, it becomes 930 millimeter, the total depth of the beam. Excuse me. That's why we have it here. On the slab, during also preliminary design, we found 175 millimeter thick. Here's the design specification. Concrete 21 MPa and steel is 400 MPa. The ACI code number 10.9.1 limited the column reinforcement to carry a load ranging from 1 to 8% only. Okay, because column is a compression member, and since the concrete is very good in carrying compression loads, therefore it is necessary in the design of column to have the concrete to be carrying the majority of the column load. That's why they have it here. Okay, let's go to dead loads. Number 1, weight of beam at 3 meter span. The formula is equal to number of beam multiplied by the volume of concrete times the weight of concrete per unit volume. The weight of concrete per unit volume is 24 kilonewton per cubic meter. Here is the 1 cubic meter of concrete. Each side has one there, and one there. So this is 1 cubic meter of concrete, and the weight for this 1 unit of cubic meter is 24 kilonewton. Okay, so that's why it's in here WC, weight of concrete. Now substitute all the values. 2 beams there times 3 meter span. This is the volume. The number inside the square bracket is the volume of the beam. 3 times 0.44 times 0.93 times 24 kilonewton per cubic meter. Cubic meter here cancel, so we solve all this together. 2 times 1.2276 times 24, we get 58.92 kilonewton. This is a concentrated load. For the column, we need just the concentrated load. We don't need the uniformly distributed load. If there is a uniformly distributed load there, we have to convert it to concentrated loads. All of the loads carried by columns are concentrated load, and it is called the axial load. That's for the column. Number 2, weight of beam, 2.5 meter span. There are 2 of them, and again same formula. Substitute that. 2 times 2.5 times, again this is the volume of the beam here that has 2.5 meter span. The first one has 3, this one now is 2.5. So we solve all this together. Meter cube here cancelled, and we solve this together, we get 49.10 kilonewton. That's the beam that has 2.5 meter span. Okay, we solve all the beams. Now let's go to the slab load. Number 3, the weight of slab is equal to the total volume of concrete slab times the weight of concrete per unit volume. So the volume concrete slab is 6 meter times 5 meter here right here times the thickness of the slab, which is 0.175 meter times the unit weight of concrete, which is 24 kilonewton. You multiply of this gonna be meter cube, cancel. The weight of slab now is, this is the magnitude concentrated load, total load of the slab. Okay, that's not uniform distributed load, is the total. It's 126 kilonewton. It's a concentrated load. Okay. Here's the definition of WC/U VOL. It's the weight of concrete per unit volume. This is the volume concrete looks like. Okay, let's get to letter B. So we have here, we have dead loads. Now letter B, superimposed loads. What are these superimposed loads? Number 1, ceiling load. Number 2, floor finished. And number 3 is movable partition. The ceiling load is allocated to 0.5 kPa and the floor finish is 0.75 kPa. I tried to analyze all these loads and they are very reasonable loads for floor finished, ceiling, and even the movable partition. Before I put it here, I investigate that and analyze it carefully. Ceiling nowadays is becoming lighter and lighter. Usually they use aluminum frame for the blocks of ceiling. They don't use anymore those heavy stuff. And the floor finished, this is very reasonable weight for floor finish. Every building has floor finished. It could be tiles, it could be carpet, it could be granite. That's really heavy, but still this is good for even it's granite or a marble. 0.75 kPa. Okay, and that's why it is a superimposed load. It is imposed after the construction. And this movable partition here is in every office building. It has movable partition, especially when they have a meeting room. The room has to be soundproof, and this is quite heavy. So this is the heaviest of all the superimposed load. I try to calculate that and investigate this load, and this is really average and reasonable. We are not under load for this amount of load here, 0.981 kPa. If you want to know the 0.981 kPa, it is 981 Newton per square meter. In 1 pound there are 4.448 newtons. So if you divide it by 4.448, the 981 divided by 4.448, that is equivalent to about 220 pounds per square meter. Okay, so that's good enough. Total SIL, is superimposed load, is 2.231 kPa. As you know, kPa is kilonewton per square meter. Since SIL is in kilonewton per square meter, we need the total area of the slab multiplied by SIL to get the axial concentrated load to be carried by the column. So the column load due to SIL therefore is equal to the total area of the slab, as shown in figure 2 right here. Total area of that times the total SIL. apply that axial right here, you get the concentrated load. So the area of slab is 5 meter times 6 meter times axial 2.231 meter square. Right here, meters cancel, we get 66.93 concentrated load. Alright, due to the slab. Now we solve the beam, the slab. The last one we're gonna solve is the live load. As we have here, letter C is live load. Okay, live load. During the previous preliminary design of slab, we calculated the live load and found to be 4.8 kPa. If you want to know how to get and calculate this 4.8 kPa, you can watch the previous video about preliminary design of slab. All the calculation is there. You gotta watch that for the live load. Okay, to get the axial load due to live load, live load axial is called the total tributary area of slab times the live load in kPa, which is this one here, the 4.8. So the total tributary area of slab is 5 meter times 6 meter times the live load 4.8 kilonewton per square meter. Live load axial. The axial live load now is equal to 30 meter square times 4.8 kilonewton per square meter. Square meter cancel. Live load axial is 100. This is concentrated load, okay? 144 kilonewton. Okay, now solve everything, the beams, the slab, and the live loads. Now let's go to the final and total axial load of the column is the summation of all these loads here. The beam at 3 meter span, the beam at 2.5 span, the slab, SIL, live load. These are the breakdowns of all the loads, and you add all this together, this summation of all these forces here, all these loads here, is the total axial load carried by the column. Is equal to 444.95 kilonewton. And there we go, we got the now we're ready to design the column. We have the final total axial load for the column to be carried by the column, 444.95 kilonewton. Okay, this is the beauty of this. Our loads here are from the real building frame. Okay, I don't recommend plugging in loads and then design your column or any members. Plugging in loads is not a very good practice when you're practicing structural design. You are really much better off just make a little drawing of frame like this, and then locate your tributary area. Any of these structural members needs the tributary area so that you can calculate the load. Plugging in loads is not very good because you don't know where those loads are coming from. But this one here, you know the source of the load. It's from the real building frame right there. This one here. Okay, so that when after you design, you feel for yourself some kind of accomplishment. You will say, oh, I designed a column there, I designed the slab there, I designed the beam there. So there's accomplishment, right? Not like plugging in loads. It's like you're not going anywhere. You have nothing to repair to afterwards, right? So that is the calculation of the column loads. This is real calculation of column loads. You can't get wrong with this. Okay, for next video we're ready to design the column. I'll show you how to design the column following some ECI code recommendations, and I think this is the end of the video, and don't forget to subscribe. Thanks for watching. Bye.